You ever been there for St. Patty's Day?
Huh?
You ever been there for St. Patty's Day?
Why New Orleans for St. Patty's?
Why not?
They celebrate everything that they possibly
Yeah,
can.
right.
Yeah, but I think like
You can
Chicago
literally
or
just,
like
like,
New York
pay
would be
some
a bit
people to
more
follow
fun.
you around and play instruments.
Because you
Like,
can
we're
actually do
virtual band for
true
the day.
pub calls then.
No, St.
Yeah,
Patrick's
Bourbon
Day
Street on St. Patty's Day is horrible. There was a guy dressed up as like a demon standing on a crate in the middle of the road, and he was like charging people to take pictures with him. That's ridiculous.
I find it funny because Mardi Gras is a Catholic, day.
Really?
Yeah. It's Fat Tuesday, but Mardi Gras is French for Fat Tuesday. You're supposed to indulge in everything that's bad before Lent, which is Ash Wednesday.
Gotcha. That makes sense.
And once Ash Wednesday starts, then you can't do any of that stuff if you follow the true rules. No one does.
So
I'm really
all for a day of sinning. Yeah.
I'm really bad with penance during
I'm trying
Lent.
to do a 1B lattice boltzmann. That has like a wall.
Oh, not his buoy. Oh, God.
Was it? No, this is.
Oh yeah.
This is. Yeah.
Oh, it's cool. I just copied and pasted.
It's alright. It works pretty well.
Like this.
Client feeling like 100 out of
I mean, is there a better one for like research?
Oh, I just like.
It's free.
Yeah, tell them why.
Yeah.
Tell them why you got it right.
Yeah, just put
That's not like
You
real
like know why you
time.
wrote on your paper.
That was so
Right.
Well, that was just easy.
It maybe takes you 15 more seconds to open up the application.
So I think I saw you.
hours to learn.
You work at Red Ops?
I feel like there was like a.
I was there.
Then what do you do?
with my family. I wasn't sure. I wasn't sure if it was you or not. Because you look. Yeah, you do.
I'm probably gonna get a little fast. What time did you come in?
I think we finally got seated at like 6.
Oh no, I was so happy with that.
Oh, you were. What? By the time I saw you, I think it was close to like 7:30. So.
You deeply offend him.
So
Last
8
minute,
o'clock
I
was
didn't
definitely like, why am I still here?
I think we left at 8.
Thanks for coming again. Those who came earlier didn't miss important instructions of everyday life that I've heard among you guys. So please prepare your homeworks to be submitted.
I'm getting it.
You have printer with you?
I do not have a printer.
Please try to bring printer next time.
Yes.
So you know what this means, Ian. You gotta hand in the computer for him to grade it.
Right. I'll get it back till next time.
Here's a time when I slowly start to
I just wanted
learn
space for
the names. And please correct me because I'm still
I didn't write
in
anymore.
the wrong.
I got really lazy.
No?
Yeah.
That makes a little
No.
sense here.
Who is Christian?
Zero.
I see green colors in both of you. Like you have on the head. He has a.
Oh, it's winter. It's fall, winter now, so I wear hats a lot more.
Sorry, my hair last night.
Hey, such a nice purple one. I woke up this morning and I was like,
Wow, that's
so. This is Dimitri. Computational class next semester.
Hi, it was you.
I was talking to Svetlana about.
Yes.
Yes.
Okay, guys.
I was. We were talking to each other, and I was making a guesses who was talking to her, and it was someone who told like I understand 0 in the physical chemistry class, and I thought like I do not know anyone who understands 0. I think highly of you guys. So Christian.
Yes.
News. So he was raising a question in talking to another faculty about the computational chemistry course, which will be offered in the spring. And during this discussion, the question was like, I'm quoting what I've heard, like, if I understand so few in the physical chemistry, is there a chance for me to perform a little bit above? Look, zero in computational.
I wouldn't go that far, but yeah.
Well, maybe I'm exaggerating, but do not worry at all. Oh, you recognize your symbol? Everyone good? Something good? I have some other pieces of paper, but probably they are.
I actually have a question on the computational class. Well,
Yes.
actually, it's kind of like, are you going to be teaching physical chemistry too?
No.
No.
Computational chemistry is not required,
Yeah, I understand that.
but it is about 10 times easier than physical chemistry, and it is 10 times more helpful in your future career.
Yeah, especially if you're going to research.
Everyone who doesn't go to the class and does lab works will have a published peer review paper by the end of the class.
Oh, okay.
Yes?
Is it based upon MATLAB, like from ground, or is it based
No.
upon the software?
It's based on software. But those who have a MATLAB background can perform like robots. Yes?
No, just discussing how exciting that class sounds.
Okay. So I will be very happy to address any questions about computational chemistry because it is much less boring than what we do right now. So it is of immediate practical help for careers. Like if you do experimental research, you are getting either beakers where you serve as a free stirring machine, or you get an instrument where you put your whatever. How do you call the little rectangular sample? Not sample, but cuvettes. Yes, you put cuvette. You push the button on the computer, and then you have a Excel file or with spectra or whatever. And then you put it in your report, or you give it to your collaborator or boss, and you get papers. With computational chemistry, you do it the same way. There is a software, you push the button, you get some figures, you basically sell it or present it. With some mumbling in the lecture time, which just gives you right language to describe what you're getting. So it will be maybe the same amount of equations, but they will be their factor in the outcome will be much less. It's just easier for instructor to rely on equations rather than clear words. But there will be homeworks will have no equations in them. But we are not in the computational chemistry class. Therefore, I am collecting your homeworks and distributing the next one. This one here.
Thanks.
This is where a person needs to be sober to not to mix two files.
That's everybody back there. Yep. Oh, I guess
Yeah,
like more too.
Green.
Actually, I woke up at 6. I Liz didn't want to go.
So I've printed 15 and didn't distribute 3. So there are 12 persons in class. Yes. Good check on basic arithmetic. So I hope you do not feel too nervous about homeworks and grades. So you shouldn't be nervous too much. So everything is good. We are progressing towards the end of the course. You should be worrying a little bit. Just the level of discomfort should be sufficient to push you through the rest of the course, but small enough so that you don't panic. So here is the next homework doesn't explicitly rely on MATLAB, but if you see a way to do any of the assignments with a MATLAB, you are very welcome to. So I don't care how you get the answers. I will just check. If you get the right answer with different approach, that's fine. What I plan to spend a little bit of time on discussing homeworks on Friday and Monday, and please prepare your questions if you feel some discomfort and need some help. So let me quickly go through and focus on what can be challenging, what is not. So this is very so this is very easy. This one straightforward. This one straightforward. This is based on extra credit from problem number 6 from last homework. This is not challenging, but takes time. This is same as we did in class and in homework, but note the imaginary unit. And this problem will help to complete whatever is here. Question A is just repeating from homework. Here you can be scared that the answer will be trivial. You may discover it without solving anything. This one also, you will be able to write the answer right away. So it's easy. For this one, there was a little part of the in-class material that I jumped through extremely quickly. So I need to remind maybe a bit of background, but mathematically there is no challenge. This one helps us to, so this question is completely mathematical. There is nothing about physical chemistry, nothing about quantum chemistry. But in about a week from now, we will face problems that look the same way. So it is, we can call it extra credit, but if you review and see some basics, some recall from your previous courses or look online how to solve this class of equations, you will make your own life in the class in what follows a little bit easier. So you see, well, not now. I will talk more about these questions on Friday and Monday, so that before next Wednesday you have enough time to prepare well. Anything looks strange from the beginning, from scratch? Anyone wants to oppose, protest? No protests. Peaceful citizens of the class. So here is our navigation map, which sites of the class material we have visited and where we are going to. And so by now we did as much as we can for free space, something with one-dimensional box, and we are getting, last time we got some background information of density metric, which is just an auxiliary tool to solve time-dependent integral equation. And last Wednesday in the lab, and in your today's homework and in today's class, we are touching the concept of density of states, right? So as soon as we will finish concept of density of states, we will go to the next level for oscillations. And right now, we are talking only about electrons. But physical chemistry is not limited to electrons. There are some other, and quantum theory is not limited to electrons. There are some other objects that cannot be described adequately without quantum properties. So we will talk a little bit about oscillations. Doesn't copyright, but you can imagine this one. Good. Those, by the way, this is the equation that one needs to do the number one from the assigned homework. You just plug in, you solve for size if you know the energy and if you know that n equals 1, right? So it should be very basic. Okay. You do have a lot of experience in quantum theory by now. You already have paradigms, and you can solve problems that bridge to real life. We are just looking forward to grow in more and more muscles and look for more and more realistic and complicated problems. And on this way, on this path, we may realize that when we are in a wet chemistry lab, or if we are in characterization lab, a material is characterized maybe by NMR spectrum, by visual appearance, by whether it is liquid or solid, or heat capacity or something like this. But if we are looking from the point of view of quantum theory, any molecule and any material is just a collection of energy levels. So it's a little bit exaggeration, but it's not wrong. You can speak. So each material is just a set of energy levels. And if typically the molecule is small, or if it is an atom, you have limited number of energy levels. The larger the molecule or piece of material that you want to characterize, the larger the number of these levels. I do not need to preach about it because you already completed the homeworks with density of states. I'm just trying to wrap up the concepts behind your successfully completed homework. So, as soon as we have more than, let's say, 10 energy levels, our just construction of a human brain fails to analyze and compare them. It is, we do not feel comfort looking at many little items and comparing them in tiny pieces. We want either to involve machines to do it, or to do something that we can process visually with some associations, some visually appealing images. Make sense? So the goal, the wish, the target is to develop a tool that will allow to compare different molecules which are represented by a set of levels. So well, if we forget about science, physical chemistry, if we are like applied math, if we get just an order, if I'm an applied mathematician and a scientist hires me, the task looks like I give you a list of numbers, which are energy levels, and help me to compare them, right? And in such way that the person who places this order will be comfortable to immediately recognize signatures of specific materials, of specific molecules, just looking on this visual representation. Make sense? So set of levels is a signature of a material. And here is an example from your homework. So we will follow the principle of ancient Romans, which was most scenic and useful in operating. If you played strategy games, computer games, if you imagine yourself like Emperor of Universe, if you took any history and main principle from divide and conquer. So it's easier, you cannot do everything at once, you need to split on little pieces. So in your homework, in your MATLAB assignment, when you developed a three-dimensional box that one axis, one side is substantially bigger than two others, and your favorite electron can move very claustrophobically in x and y, but moves almost free, well, not almost, but much less confined in z direction, then movement along x and y gives big offset in energy. That's it. But movement along z direction can be associated with several eigenstates at different energies and energies offsets. And you have seen, now you probably are convinced through the homework that if you have one-dimensional material, then there will be a set of features in the density of states that is asymmetric peak, and to the right of the peak it decreases approximately as 1 over energy or something like this. Make sense? It is what you've seen and what you have reported, submitted. Now we want to dig deeper what it is, where it comes from, and derive this equation. Okay. If you are not sitting in a class and watching it on the video recordings, you can skip all wordings before and just read this text. So just combine a set of levels into continuous distribution. Today we will set up definitions and apply it to a case of one-dimensional box, hopefully. And next time we will apply 2- and 3-dimensional boxes, so that figures from your homework will be reproduced by pen and paper, by pure theory. Again, we will imagine that we are little supercomputers, but without more thinking on the human style of processing trends rather than silly going from point to point. So let's recall. the energy of level number n in one-dimensional blocks. N squared and the rest of garbage, which is, Brennan wants me to help him power here, right? Thank you. H bar, which power? Well, do not laugh right now. Try to remember it in a year from now. Or in 20 years after you undergraduate course. But we can call it as E0 times n squared, so that we do not think much about these constants. So which well, let's do E sub n divided by E0. So which energies, those are, I would say, normalized energies, so that we do not care about this factor E0. So which values of this normalized energy are allowed if you want to put them on the x-axis? If you have a progression of n equals 1, 2, 3, 4, 5, then this En over E0 will be what?
1, 4, 9, 16.
Squared 1, 4, 9, 16, and the rest is too complicated. 1, 4, 9, 16. Okay, only for you, 25. Now, how can we where should we go further? We can define number of states, number of levels that have energy less than a threshold. States with energy less than given threshold. How many H's in this word? 2 or 1? Huh?
One after the T.
Yeah.
Something got H.
Double H or single H here?
Like single.
How can we call it? So number of states, threshold, what? Number of states with energy less than given threshold. So if I'm traveling across the diagram, or if I'm making an experiment where I'm continuously increasing the energy. I don't know if I will show anything valuable on the screen, but better focus on it. So if I'm traveling across the energy and looking back, how many energy levels are left behind my back? Make sense?
Can you repeat that?
Huh?
Can you repeat that? What did you say? If you're
How-
traveling.
How I'm traveling? Yeah, where I'm traveling. I'm traveling along this axis. Forward.
It's a human sense of electron.
And then I'm looking backwards and counting how many levels are behind me. And then I'm making a table, a little notebook of my travel. So if I am staying before 1, I have 0 states behind me.
0 energy thresholds.
Well, I am at threshold.
Oh, yeah, so if you're at threshold 1, you're looking back, there's no previous
Right.
threshold, so
Yes.
it's 0.
Yes, 0. If I'm crossing 1, it will be 1 state behind me. If I'm crossing 4, there will be 2 states behind me. If I'm crossing 9, there will be 3 states behind me. I'm crossing 16, there will be 4 states behind me. So on the x-axis, we have something related to energy. And on y-axis, we have something like number of levels. If we swap this axis, it will be like quadratic function again. But this is really something important. I want to bring your attention to the thing in the following context. We can make a mathematical experiment and take derivative of this function. This one is function of energy. So let's, I don't know how to erase things. And if I will start writing over, we all will get crazy. Maybe just next page. But the figure will be there. No, okay. Good. So we have a set of steps, right? And now we do want to define derivative of number of states over the energy. How does the derivative of step function look like? We have only one person who can help us in the audience.
Delta function?
Huh?
Is it a delta function?
Okay, 2. So the jump discontinuity in the function means that there is a infinitely high pike at the same energy, right? 0, 0, 0, then another pike. 0, 0, 0, then another pike. 0, 0, 0, then another pike. Energy, and here we have this derivative of number of states over energy. Derivative of number of states over energy.
So, like the 0-dimensional box or the 0-dimension graph, that's what that graph is showing.
Yes, exactly. And if we will turn our heads by 90 degrees, you will see that those are just energy levels, right?
Mm.
So there's something related to problems that we are solving. But we are still, we developed some crazy new concepts, but we still are not too far towards our goal. We do not have visual image that will combine thousands of levels, but we are very close. If we are thinking as, not as machines, but as programmers who prepare these machines to run, in fact, your density of states, which is defined exactly this way, this is definition. Density of states, and we are not yet ready to define it fully, but I will return to definition again and again. Density of states is number of states per energy interval. Nothing is wrong with the definition. You can memorize it. So number of states per energy interval. Well, if I perform a zoom out, well, of course we can do it literally here for this figure. But if I do it just in my mind and I stay off this image very, very far and look the continuation of this progression, then this initial part of image, they look like states, levels are very close to each other. And when my vision is not very sharp, or the just bullet points on the screen are not well resolved, the peaks will merge together sooner or later. If I'm thinking as a physical chemist, I will understand that all these abstract things have limits. In fact, any realistic model experiences thermal motion of all atoms around, and energy levels are shaken a little, which brings thermal width for any energy level. And we can take into account this fact by assigning some non-zero width, well, same width to all of them. Okay. And then, if we add these profiles of non-zero width for each energy level together, we are going to come into continuous distribution, which will look like set of individual peaks in this case, but if the levels will be very dense, it will generate a continuous line. Make sense? Now let's wrap it up with some equations. So this is energy 1, energy 2, energy 3, energy n, and we want to define, to set an alternative definition of density of states. Instead of making a literal derivative of number of states behind myself, I can take that each delta function, and density of states is function of energy, minus energy of given level, and then I add together all these functions. With understanding that delta function is an abstraction, instead we will do like Gaussian function or Lorentzian function that have finite width function. Make sense? And it is what you guys did in your homework. So you implemented this equation and then plugged in different set of levels and saw how this procedure generates different continuous functions. So from now on, you know what is density of states. You do know the definition. You are ready to write similar codes if needed. But we still are not too close to the pen and paper derivation. How can we check that it is 1 over energy and not 1 over energy squared or 1 over square root of energy? Or maybe something more, maybe another function. If we come to professional activity and we see several objects of the similar spectrum, we may want to have some reference point. We can perform successfully without this luggage of theoretical garbage, but with it, the life becomes a little easier. So we do want to see what happens to this green line in the limit when energy between state n+1 and energy between state n goes to 0. How does this green distribution behaves in limit of infinite number of levels or continuous distribution of states? Okay, this is summary of what we did. This is also summary of what we did. So if you have one step, then some people call it with theta symbol, like delta if it is a spike and theta if it is just step by one. And here is the definition that you can see on other screen, that we set up right now. So energy minus energy of level summation. And we can replace it by our favorite function, Gaussian distribution with a fixed width, where width can be selected, for example, based on room temperature. So what if the levels are denser or width is bigger? So instead of peaks, we will have a continuous line. And you see, as further away we are from origin, the more is offset between nearest levels. So the density, number of states per energy interval decreases, right? And it is what we saw on the figure at the beginning of the meeting. So this function will go down, but right now we have some structure. Can we get some really solid mathematical function for this decrement? So I'm going to do the same thing as we did in discrete space, with understanding that now we are coming into limit of very dense states. So we can set up dependence of energy as function of the number of levels. This will be n squared, right? But for our definition, for derivative of number of states per energy interval, we need dependence of number of states as function of energy. So we need to inverse this function. How do you inverse functions graphically?
Flip it over the x, y equals x.
Not x.
Y equals x.
Huh? Y equal x. Yes, yes. So if you had exponential growing, then logarithm is growing with different pace, right? And if you do the same for quadratically growing function, for energy as function of number, then inverse function n as function of energy will be what? Inverse of quadratic function. E divided by E0 in which power?
1/2.
Yes. Square root or power 1/2, right? So now we are repeating the same steps we did in discrete space, but in continuous space. So number of levels behind myself, in case the levels are very densely packed, is square root of energy. Good? Now we are, so here is number of states, here is the energy. Square root of energy divided by ground state energy. So the only thing we need to do is to practice definition. dN over dE. So we need to take derivative of square root of energy. How do we take these derivatives? If I forget. So power n after derivative becomes, how does power change after derivative? Increases or decreases?
Decrease.
By how much?
1.
Huh?
1.
By 1. So 1/2 minus 1 equals minus 1/2. And the factors comes up front, right? So it will be 1/2 square root E0 e to the power minus 1/2. Right? And if you have something to the power minus something, it is just inverse, right? So we understand this minus 1/2 power as 1 divided by square root of energy. See? So there were no tricks. We went through the same path 2 times. Once in discrete space when we have few levels, and another one in continuous space when they are just running number as a continuous variable. And then this density of states is 1 over square root of energy. How does this function look? It is same like 1 over energy, but it is a little more softer. And let's see. So we do have decrement of density of states as function of energy, and this is universal relation. So for any one-dimensional object, you'll see signatures of this 1 over square root of energy trends. So no matter whether it is based on carbon nanotubes, or based on some fancy, I don't know, silicon nanorods, or each other semiconductors, like modern perovskite nanorods, for all of them. If, by the way, there is an experimental way of measuring density of states by so-called scanning tunnel microscopy. You just measure it and get this 1 over square root of energy trend. So you are going into true life, nanoscience, physical chemistry. So here's what we derived in class. Here's what you got in your homeworks, right?
Mm-hmm.
So the only thing that we started from the offset, which is energy of ground state for this direction of motion plus energy for other dimensions, like for x and y. So it is, the offset is a little bigger. Yes?
How does this apply to the region of like the homo-lumo gap?
Did you get the question? We are looking only on LUMO. There is no HOMO in this treatment. So we are dealing with only one electron. And if you would have many electron systems, then the HOMO or whole states, absence of electron, would go from Fermi energy Fermi, in a different direction. And then the density of states would look this way. So here is for electron, here is for holes.
So we're basically looking at this electron in a ground state that's this energy state.
Well, yes, if we are in a ground state of multi-electron system, we are looking for possible excited states of only one electron, when the rest of electrons stay in the ground state.
Yes.
And then for them, you will rediscover this 1 over square root of E energy trend. So while going to higher energies, density of states drops. with this, we are done with one-dimensional box laser states. Moving forward to see you tonight for labs. The thing that we will do tonight will, if you will wait packets, that we will pursue for several weeks, and it will be a base for presentations in 3 weeks from now.